Hey students, Professor Nugent here. In the last video, we discussed constructing a test statistic to test a hypothesis about the slope of the regression line beta 1. And we saw that testing a hypothesis about the value of the slope is equivalent to testing a hypothesis about the value of the mean. The test statistic is the difference between the estimated value and the hypothesized value divided by the standard error. We compare that test statistic to the critical value based on a standard normal distribution, or we compute a p-value and compare the p-value to the significance level. In this video, we are going to discuss the construction of confidence intervals for beta 1. Recall that a 95% confidence interval is equivalently the set of points that cannot be rejected at the 5% significance level, or a set valued function of the data, which is an interval that is a function of the data, that contains the true parameter 95% of the time in repeated samples. So, what we need to say is that in 95% of all possible samples, we believe that the true value of beta 1 will reside within the range of the data that we define or that we estimate. And that set of points within that range cannot be rejected because we're saying that those set of points 95% of the time, or beta 1 is among those set of points 95% of the time. Because the t statistic for beta 1 is distributed according to the standard normal distribution in large samples, construction of the 95% confidence interval for beta 1 is just like the case for the sample mean. And that means that the 95% confidence interval for beta 1 will take this form. Okay? We'll have the estimate for beta 1 hat plus or minus 1.96 times the standard error of beta 1 hat. Okay, that's where we will get our 95% confidence interval. And we're saying that we believe that the true value of beta 1 lies within this range of data. We are also saying equivalently that the t statistic will reject a hypothesized value whenever the null hypothesized value is outside this range of data. Okay? So we believe beta 1 to be within this range of data, and if we hypothesize a value about beta 1 and it is outside this range of data, then we will reject that hypothesized value. Let's see an example about constructing a confidence interval using our test scores and student to teacher ratio. We've seen this regression line that test score is equal to 698.9 minus 2.28 times the student to teacher ratio. We have that the standard error of the intercept is 10.4. The standard error of the slope is 0.52. So we can construct a 95% confidence interval for the slope. Beta 1 hat plus or minus 1.96 times the standard error beta 1 hat. That's negative 2.28 plus or minus 1.96 times 0.52. That gives us a range, which is negative 3.3 and negative 1.26. We believe, or we can say that we are 95% confident that the true population slope resides between negative 3.3 and negative 1.26. Now this 95%, the fact that this 95% confidence interval does not include 0 means that the hypothesis that beta 1 is rejected at the 5% significance level, and that is because we're saying that in 95% of all possible samples, beta 1 is never equal to 0. And so it is rejected at the 5% level. Right? We're saying in 95% of all possible samples, beta 1 is between negative 3.3 and negative 1.26. In 95% of all these possible samples, it's never equal to 0. So we reject that hypothesis at this confidence level, which is equivalent to this level of significance. Recall that significance is alpha, and confidence is 1 minus alpha. Okay? So a hypothesis test with a 5% level of significance will, by definition, reject the true value of beta 1 in only 5% of all possible samples. And so in 95% of all possible samples, we will have that the true value beta 1 will not be rejected. So this is an important conclusion to understand. We can take from this a concise, which is the conventional way to report regressions, which is to put standard errors in parentheses before the estimated coefficients to which they apply. Alright, so the regression is test score is equal to 698.9 minus 2.28 times STR, and we have put the standard errors in parentheses below the regression coefficients. Also note that we are reporting R squared and the standard error of the regression. So this is the way that we are going to report regressions from now on. Let's look at some data output. We have our standard. We are familiar with the reading the coefficients, right? The R squared. What's new for us is the standard error. Right? We have the standard error of beta 1 and the standard error of the intercept, beta naught. We get the t statistics and the p-values for the null hypothesis that these coefficients are equal to 0. The two-sided test, okay? And we can see, based on the p-value, that the coefficients are statistically significant because the p-value is smaller than 0.05, so the coefficient is statistically significant at 5% level of significance. The p-value is also smaller than 0.01, so the coefficient is statistically significant at the 1% level of significance. Finally, we have a confidence interval for our estimates. We believe that the coefficient of the slope of the regression line is between negative 3.3 and negative 1.25. Likewise, we believe that the intercept is we are 95% certain that the intercept resides, the population intercept resides between 678.56 and 719.305. Okay, and that these are the 95% two-sided confidence intervals. Let's summarize the statistical inference methods about beta naught and beta 1. We are using OLS estimators, beta naught and beta 1. They have approximately normal sampling distributions in large samples. So we are going to use the standard normal distribution as the benchmark. We will typically use a two-sided null hypothesis. We will test the value of beta 1. We will have a null hypothesis that beta 1 is equal to some value. Typically, we are testing that beta 1 is equal to 0 to test its statistical significance, versus the alternative hypothesis that beta 1 is not equal to that value. We have a test statistic that is the difference between the estimated value and the null hypothesized value divided by the standard error. We use the test statistic to calculate the p-value, which is the area under the standard normal curve outside or beyond the test statistics. For the using the standard normal curve, right, beyond the positive and negative of the test statistics. The confidence interval is the set of beta 1 that is not rejected at the 5% level. So the 95% confidence interval contains the true slope in 95% of all samples. And we calculate the 95% confidence interval using the very same method that we do for calculating a 95% confidence interval about a mean. And I think it's important, intuitive, to recognize that the t-statistic will reject any hypothesized value when that hypothesized value is outside this range. So whether the hypothesized value is 0 or some other value outside this range, the t-statistic is going to reject that, because that hypothesized value is because we are not confident that in 95% of all possible samples, the true beta 1 can be equal to that value because it is outside of this range. Alright folks, that is it for confidence intervals and statistical inference about beta naught and beta 1. In the next lecture, we will discuss regression when the independent variable is binary.